Welcome back to Nature and Code. We're in chapter 7, and we just implemented our epidemics spatial spread model. But rather than having a pure grid, we implemented a small world type of grid where we had occasional jumps, um, you know, from one individual, a contact to another random individual, rather than two individuals just in the, you know, near neighborhood, near proximity. And we saw that a consequence of that is that when outbreaks occur, they're usually much larger, like this one here, that probably infected, yeah, I would say somewhere in the vicinity of 65, 70%. Now, let's go ahead and quantify this. Rather than just making an argument based on some visuals in a simulation, let's actually use our code to quantify this. So if we go to our code, um, let's take a look at this here. We have the set interval that says, calculate this, and then every 50 seconds, run the time step and update the grid. Now, this is something I would like to remove. Okay, I'm just going to remove this because I don't want to, use a visualization anymore. Also, we can remove the draw grid, wherever you have that in your code, basically just go ahead and remove it. So now we need our simulation to run without visualization. So now that we don't have this pacemaker, so to speak, of set interval, we have to basically do this on our own. And what I would like to do is I would like to run not just one simulation, but I would like to run many, many simulations and then calculate the average of the outbreak size. So how could I do this? Well, first of all, I need to define a function that runs a simulation, and I'm going to call this function run simulation. And what this function does is it initializes the grid. And you know what? Let's get rid of the init grid up here because we don't need that anymore here. Okay. It initializes the grid. And then once it's done that, I'm going to say while a certain condition is true, which I'm going to define, then run this run time step method that we implemented above. And I want this, so how long do I want this to run? Well, basically I want this to run as long as there are infected individuals around, right? Because as long as there are infected individuals around, there's a chance for more spread. As soon as there are no more infected individuals around, well, then we can stop the simulation. So I'm going to say here, while get number of infected, and this is a method that I will have to implement, but I assume it will return the number of infected individuals. So while this is larger than 0, implement this. Run this time step. So let me go ahead and implement this function. Function get number of infected. So how, what does this function look like? How should it work? Well, I'm simply going to go through all the individuals. So I'm going to use a two-dimensional loop, and I'm just going to copy one here that I use up here. So I'm going to copy this. Okay, so this is our regular for var I smaller than grid length, and so on, and then var I smaller than grid length. I'm going to say if a grid I equals capital I, so if this is an infected individual, then I need to increase some counter. I'm just going to call this here counter. So then I'm going to, up this counter by 1. Counter plus 1. And need to make sure I close these loops correctly. And at the end, I will simply return counter. Now, I might later want to have a function that is called get number of recovered or get number of susceptible. So, I might just do this a little bit more generically, let's say. So I'm gonna instead rename this function here get number in state, and I'm gonna let state be a parameter. And so, now specifically this counter is really sort of the number in state. I mean, you could call this counter, but I'm gonna, just rename this to number in state. And now the state here will either be S or I or R. So I'm gonna compare it to this state. Okay. And now this is a much more generic version. So return counter. Now I can simply say get number in state and then pass in an I, or pass in an S, or pass in an R, and it will give me the number of individuals in that given state. So this is much more generic. Somehow I still like actually the name of this function. So I could just define here these convenient functions, right? Which would be get number of infected. But rather than implementing this from scratch, I could basically just say, well, you know what? Just return whatever this function here returns, get number in state I. Yeah, so now this function simply delegates it, passes the request on to this function with the corresponding parameter. And now if I would want to define a function called, for example, get number of recovered, then all I would have to do is change the parameter here. And of course, I could also define one for susceptible if I decided I would ever need this. So these are sort of convenience functions. Get number of susceptible, and this would of course now just ask for the number of individuals in state S. All right, so this should now work. So I can just call this function run simulation, and as long as there are individuals in state I, it will run this time step. Okay, so if I just wanted to run one simulation, I could just now call run simulation. But I said I would like to run many simulations and then calculate, how many, what the outbreak size is. So what I'm going to do is I'm going to define first an empty array where I'm going to store my data, which are the outbreak sizes. And then I'm going to set up a loop. So for var I equals 0, I smaller than number of simulations, and this is however many simulations I want to run, I equals I plus 1, I will call this function. Okay, so let me define here this variable number of simulations. And let's say, I don't know, how many should we run? Maybe 100? Okay. And, now we can say, once that is done, I would like to, know how many people or how many individuals got infected. How would I know this after the run simulation call has executed? Well, as we've seen before, once a simulation stops, everyone has recovered, right? Because we keep it running while there are still some infected individuals around. So once everything, everyone has recovered, and previously when we visualized this, the part of the grid was green, we just have to count how many recovered individuals we have, because that is the number of people that have been infected, right? Because each of the recovered cells has once been an infected cell. So now I can simply say, this is what I'm going to push into my data array. Data push get number of recovered. And this will now, simply go through the grid and see how many of the cells are in the recovered state. And that corresponds to the outbreak size. So let me clean up this here a little bit. I want to take these variables here and just, in light of good styling, I'm going to put these here at the top where I define all the other variables as well. So now all I can do is basically here at the very end, once I've done this, just simply say, you know what, just show me what you have here in the data array. Okay. So if we now save this and reload the browser, we shouldn't see any simulation anymore, but we should see the results of many simulations. And this might take a few seconds, but eventually it works. And so here you can see many of the simulations are actually quite small, sometimes even just one, which makes perfect sense, right? As we've seen before, patient 0 might recover before it gets a chance to infect others, but sometimes they go really big, and if they do, they go up to 6,000 or 7,000 individuals. Now, keep in mind, we still have our small world here. How can we change this to small world? Well, we could simply, or how could we change this back to not small world? Well, we could simply set this to 0, right? Then this would never happen. This here would never happen, and it would always just try the regular infection of the local neighbor. So you know what? Let's go ahead and define this here as a variable. So let's call this rewiring probability. And we will of course have to define this here as a variable. And now we can say, okay, if this is 0, oops, should be nice and use var, then we have a perfectly spatial grid, no small world. If it is a small number like 0.01, then we have a small world with 1% rewiring. But let's set this to 0. Let's set this to 0 and then save and reload. And again, this is going to take a few seconds because we're running a lot of simulations. So this is interesting. Again, we see quite a few simulations that don't go beyond patient 0, but sometimes they do. But then they tend to be much smaller. The biggest one I can see here, here's a fairly large one, 5,000. But the others are all sort of in the 2,000, 1,000, or even just a few hundred. So let me reload this. You can already see here from these numbers, well, okay, here we have a couple that are actually go into 2,000 or 3,000. But it seems to me already quite obvious here from these numbers that without the rewiring, these outbreaks tend to be smaller on average. But you know what? Let's just go ahead and calculate the average, right? We have our data array, and our data array, we can just pass it to a function that calculates the average of the values in here. So let's go ahead and do this. So down here, why don't we define a function that we're going to call calculate average size. And it's going to require an array, and I'm going to call that data, an array with the values. And so what it should do is basically it should just go through all the values and then calculate the sum of these values and then divide by the number of values. So this is fairly straightforward. For var I equals 0, I smaller than however many values I have, so this is the length property of the array, I plus plus. And I'll explain this in a second. So here I'm simply going to say sum plus equals data I. And I will also explain this in a second. So this is now the sum. So now I will return sum divided by data length. And this is the average. Okay, so now rather than doing a console log on the data, let's do a console log on whatever this function returns if we pass the data. Okay, so again, without rewiring, so a perfectly spatial world has an average of 431. Let's do this again. 300. There's obviously going to be quite a bit of variance. 494, but always sort of in the 400s. Okay, let's go back. Let's set this variable here now, rewiring probability to 0.01 to create the small world type of simulation. Save and reload. And what we get now is 2,922. 2,767. So you can see now from these numbers, indeed, the average outbreak size is about factor 6 larger, simply due to these rare, occasional random chumps. That's quite remarkable. Now, one more thing. Let's take a look at this function here. I said I'll explain this in a second. The time has come now to do this. What is this? And what is this? Well, these are shortcut operators. So far, we have always done the following. Whenever we wanted to add, 1 to a value, we said something like I equals I plus 1. And that made a lot of sense, right? You take what you have in I, because the right-hand side of this equal assignment gets executed first. So you take what you have here as I, you add 1, and then the result of this sum will be stored into I. And so now I has increased by 1. But because this is such a common thing to do, the JavaScript language designers decided to have this plus plus operator, which is the exact same thing. It just increases the variable by 1. There's also minus minus, which decreases the variable by 1. And indeed, these are actually shortcut versions of a more generic shortcut, which is the following. Let's say you wanted to add to I, something, let's say x. Again, this makes perfect sense, right? You take what you have in I, you add x, and then the result of this sum will be stored back into I. So now you've effectively increased I by x. The JavaScript shortcut for this is I plus equals x. So that, so that we don't have to write the variable name twice. And this is exactly what we do here. Rather than saying sum equals sum plus data I, we just write plus equals. And you can use these for all operations. So when you say minus x, you can write minus equals x. When you want to say divided by x, you can say divided equals x. And when you want to say times x, you can simply say times equals. Now, again, for the special case where x happens to be just 1, which is very common in loops, you can use an even shorter version. So, if x equals 1, you can use this version. Sort of the shortcut of the shortcut. Okay, I hope this makes sense. And, from now on, I'm just going to use this shortcut. You can ask yourself, well, why didn't you introduce this shortcut in the very beginning? Well, basically, I didn't want you to, I didn't want to bother you with shortcuts. I think shortcuts are great once you really understand what's going on. But I wanted to make sure you first have a very solid understanding of what's going on before introducing shortcuts. But these are very handy shortcuts, and I certainly want you to be aware of those, because if you look at code, JavaScript code that's written by other people, these shortcuts are all over the place. All right, and this concludes this video, and it concludes this chapter. So we have seen how an infectious disease can spread in a population through space. We have seen that this will always be a balance of, infection that's going on at a certain speed and recovery that's going on at a certain speed. And we have also seen that much depends crucially on the underlying contact structure. And we have now looked at two simple but common contact structure. One, perfectly regular grid where everything is completely local. And then the second structure was a slight change. We occasionally would rewire contacts, so to speak, to other random locations. And this creates the so-called small world, because it makes the world much smaller, because each cell is now much closer in terms of numbers of contacts to any other cell. But this has profound consequences for an infectious disease spread, in that infectious diseases spread faster, but also, as we've seen, because of that, they will infect many more people than we would expect if everything was just completely spatial. All right, so I hope you enjoyed this chapter as well. And, you certainly come a long way, and you now understand much about biology, about nature, the evolutionary processes. And now in this chapter, we've also looked at a process that is highly dynamic, not directly evolutionary, but highly dynamic, the spread of infectious diseases. In fact, we're not going to talk about this in these videos, but of course, when you think about infectious diseases, evolution plays a key role. And just to give you one example, if you think about bacteria that are becoming resistant to our drugs, the antibiotics, which is now a huge and growing public health issue, and that, of course, is the direct consequence of evolution. Excuse me, and of coevolution, to be more precise. So we came up with these drugs, and as we've seen in the coevolution videos, the bugs have a strong fitness pressure, a selective pressure to find a way to make these drugs useless, so that they can still reproduce quickly, even in the presence of these drugs. Again, there's no guidance, there is no wanting anything by these bugs in terms of evolution, but any mutant bug that is not affected by the drugs will instantly have a substantial fitness advantage, and will then spread in the population. And this is exactly what we're seeing now as a growing public health threat. So again, this chapter is now concluded. We'll have more chapters in the future. The next one, as in the book, will be about the emergence of cooperation. I'll see you there.